Welcome to the content material for Class 2 of Engineering Statics. You should be watching this video before your second class. Today, we will be covering several important ideas that will provide a foundation for this course. In this lesson, we will cover the following topics: fundamental quantities and the units of measurement, types of objects that can be considered in mechanics, Newton's laws, and numerical accuracy. The first thing we'll do is define mechanics. Mechanics is a branch of the physical sciences that is concerned with how objects move when they are subjected to forces. And mechanics has many different fields depending on the type of object that is studied. There are four types of idealized or simplified objects: particles, rigid bodies, deformable bodies, and fluids. In mechanics, a particle has a mass, but its size can be neglected. All of the forces act through the center of gravity of the object in a particle. The size is relative to the dimensions and forces. So for example, the Earth can be modeled as a particle because it is small relative to its orbit. Or a small ring can be modeled as a particle since all the forces meet at the point in the middle, or the center of gravity. This is the simplest object to study, and we will start with particles in this course. A rigid body is an object that cannot be considered a particle because it is larger or because the forces are not through the center. In a rigid body, the forces do not act through the center of gravity. So for example, this rod has forces acting on the left side and on the right side, and these forces may cause the object to rotate. However, in a rigid body, the object is rigid and it will not change shape. So, as you can see, depending on the type of objects that you're considering, will determine the field of mechanics in the course. In this course, we will only be studying particles and rigid bodies. This course will only study objects that are in equilibrium. They are at rest or they are moving at a constant velocity. We call this course statics. Once these objects are in motion or accelerating, it is called dynamics, which is another course you may study in the future. For civil engineers, the mechanics of deformable bodies is very important. For example, steel structures experience stress and strain when exposed to a force. And in the future, you may study fluid mechanics. Civil engineers often work with water, which can be assumed to be incompressible. However, many chemical engineers will work with other fluids, which have to be considered compressible fluids. Fluid mechanics with compressible fluids can become very complicated. Another idealization that we will make in this course is called a concentrated force. We will assume that forces are concentrated, which means the area they act on is small. An example might be in this train wheel. The force acts on a very small area in the wheel. Engineering mechanics is formulated on the basis of Newton's three laws of motion. Newton's first law says that a particle originally at rest or moving in a straight line with constant velocity will continue to do the same thing, provided that the particle is not subjected to an unbalanced force. In other words, as long as the total forces remain in balance with each other. And we call this equilibrium. Newton's second law says that a particle acted upon by an unbalanced force experiences an acceleration that has the same direction as the force and a magnitude that is directly proportional to that force. Newton's third law is the action-reaction law, which states that if one body exerts a force on a second body, then that second body will exert a force on the first one, which is equal in magnitude but opposite in direction. Another important thing for us to understand are the fundamental quantities that we can define everything in when we're measuring. So for example, the fundamental quantities are mass, length, and time. From these fundamental quantities, we can create derived quantities. And the most important one is force, which we will use in this course extensively. Force is related to mass by Newton's second law, which says that a force is equal to mass times acceleration. So, force is equal to mass times length divided by time divided by time. And there are other derived quantities such as area, velocity, acceleration, pressure, and angles. But all of these can be defined in terms of the fundamental quantities of mass, length, and time, as shown here. And these quantities are important when checking your work. If you're adding things together, or you have two quantities on two sides of the equation, they must have the same fundamental quantities. So for example, if you have force on the left-hand side of the equation with units of mass, length per time squared, you need to have the same units on the right-hand side of the equation. And then these quantities need to be described and can be described in different systems of units. The two systems generally used are the SI system and the US customary system. Let's consider length, time, mass, and force as the quantities. In the SI system, the basic unit for length is a meter. However, in the US system, the unit for length is feet. The units for time in either system is seconds, and for forces we can use newtons in the SI system or pounds in the US system. And a newton is defined as a kilogram times meters per second squared, or mass times acceleration. On the other hand, a slug in the US system is defined by dividing a pound by acceleration, or pound times seconds squared divided by feet. We will not use the US system too much in this course. In the SI system, we use the following prefixes. There is a giga, which is 10 to the 9 of whatever unit. So gigameters or giganewtons, for example. And then there is mega and kilo. Of course, we're familiar with kilograms and kilometers, meaning 1,000 grams or 1,000 meters. And there's also milli, micro, and nano, representing smaller quantities. So let's look at an example where we convert kilometers per hour to meters per second, and then also to feet per second. So let's start with 60 kilometers per hour. We know that there are, in 1 kilometer, there is 1,000 meters. And we know that in 1 hour, there is 60 minutes. And in each minute, there is 60 seconds. And what we see here is that we can cancel out the units. We have an hour here and an hour there. We have a kilometer here and a kilometer there. We have minutes and minutes. And we see that ultimately we end up with meters per second as our units. And once we do the arithmetic, we see that the answer is 16.67 meters per second. So if I report the answer using 4 significant digits, it would be 16.67, or we might choose to write it as 16.7 meters per second. Now if we want to convert this answer to feet per second, we then need to convert this answer. So let's start with 16.67 meters per second, and then we're going to have to convert meters to feet. So I know that there are 1,609 meters in a mile, which is 5,280 feet. You might remember or be able to look up a different conversion number, but again, the key is that we have the units cancel. So we see meters and meters cancel. And once we do the arithmetic, we find that the answer is 54.69 feet per second. The last thing we will talk about today is significant digits. Significant digits are the non-zero numbers in a value starting from the first non-zero digit. Significant digits are important for your answer. You don't want to include too few. If you use a lot of rounding, the answer will not be accurate. On the other hand, reporting a long list of significant digits is not appropriate, since we don't have that level of accuracy. For example, we don't want to say something like 6.2549222 meters. This is way too many significant digits. Normally in this course, we will use 3 to 4 significant digits. So let's do some examples. Let's imagine you do a calculation and you read on your calculator the answer 27.29543. If you want to report 3 significant digits, what's the answer? Well, you should be writing 27.3. We round the 2 up because of the 9. Now how about 4 significant digits? Well, that answer would be 27.30. We see that the 9 gets rounded up because of the 5. And so we would report 27.30, giving 4 significant digits. In another example, if we read 0.0675503 on our calculator, well, for 3 significant digits, that would round to 0.00676, again because the 5 rounds up. So in this case, we ignore the zeros until we get to the first non-zero, and we see that is a 6 here, and that becomes the first significant digit. So if it were 0.00676 kilometers, we could convert that by multiplying by the ratio of 1,000 meters in a kilometer to get an answer that was in a more suitable set of units. So if we say 0.00676 kilometers times 1,000 meters in a kilometer, we would see that we could also express that as 6.76 meters, which is a nicer answer using 3 significant digits and an appropriate set of units. Okay, so that's it for Class 2. Be sure to come to Class 2. We'll have a quiz on this material. See you then.